Hello viewers, welcome to video number 96 of the channel MALACHEMPHILIC, and video number 96 is the 37th episode of Chemical Thermodynamics, and topic of this episode is entropy, third part, and here we will discuss entropy as a state function. That means the proof for state function of entropy and the relation between entropy and internal energy as well as entropy and enthalpy. So let's start. In my earlier videos, we have seen that where I have discussed this entropy, we have seen that entropy change delta S is Q by T. And by definition, this entropy change is the heat exchanged reversibly isothermally divided by the temperature at which this heat exchange occurs. Why reversibly? Because we have seen that this formulation of entropy has been derived from Carnot cycle where all the steps are reversible. And isothermally, heat exchange occurs in isothermal process. And let me recapitulate little bit. We have seen that efficiency of the Carnot engine, that is equal to Q2 minus Q1 divided by Q2, where Q2 is the heat absorbed by the engine from high temperature source. Q1 is the heat release to the low temperature sink, and eta is also equal to T2 minus T1 by T2. Already I have discussed all these things, so let's go little first. So therefore we can write these things is equal to 1 minus T1 by T2. So these things cancel, and then we'll get eta is equal to these things, that is Q1 by Q2, and that is equal to T1 by T2. So from this equation we can write what we wrote: Q1 by T1 is equal to Q2 by T2. So Q by T term is a constant. This is constant. It is another thermodynamic quantity, and this is equal to the change in entropy of the system here. Now, in Carnot cycle, heat is absorbed from the high temperature source. So that means plus Q2 by T2, and that will be is equal to heat is released to the low temperature sink, that means minus sign. Q1 heat is released. From this equation I am writing, that is T1. So from here we can write that Q2 by T2 plus Q1 by T1 is equal to 0, or summation of Q by T is equal to 0. That is that the summation of all heat exchange divided by temperature, this term of a Carnot cycle is 0. Now let's prove that entropy is a state function. So we are going to prove that entropy is a state function. State function means that change of entropy, which is delta S, it depends on the value of initial and final state and is independent of the path followed. Right? Now, for that, let us consider system is in state A. right? Now from state A, it is going to state B, okay, via path 1. This is path 1. Then once again it is a cyclic process. So once again it is coming back to A via path 2. Okay. So system is going from state A to state B, state change, via path 1, coming back to state A via path 2. Now this cyclic path, we can consider it as consisting of large number of Carnot cycle. How? See, this is A. Okay, large number of Carnot cycle. Carnot cycle, we have seen that first step is the expansion, then again expansion, then contraction, contraction. Again expansion, expansion, contraction, contraction. Again say expansion, expansion, contraction, contraction. So this entire cyclic part, we can consider that it is consisting of a number of Carnot cycle. Okay. If this each step or each Carnot cycle is very small, that means entire path is consisting of a large number of small Carnot cycle. Okay. Already I have shown you. Expansion, expansion, contraction, contraction. Expansion, expansion, contraction, contraction, like Carnot cycle. Now, one thing you try to observe here, expansion, expansion, contraction, contraction, again expansion. That means, see, in this middle path, one time it is expansion, one time it is contraction. Okay, expansion, expansion, contraction, contraction. That means one time it is contraction, one time it is expansion. So middle paths are getting cancelled. So if the middle paths are getting cancelled, what is left over? This zigzag path. Now, if it is consisting of a large number of Carnot cycle, then zigzag part will be very small in the sense very close. Then this zigzag path will be almost equivalent to this cyclic path, that is A to B and then B to A. Okay. Now, already we have seen that for a Carnot cycle, this Q by T, summation of Q by T is equal to 0. Heat exchange divided by temperature, that summation is 0. So for one Carnot cycle, if it is 0, for an infinite number of Carnot cycle also it will be 0. 0 plus 0 plus 0 plus means for a large number of Carnot cycle also it will be 0. So what we can write this path, that is integration of A to B, then del Q, I am writing here, we can write reversible because Carnot cycle all the paths are reversible path, okay, reversible by T plus B to A, integration of B to A, again del Q reversible by T, that is equal to 0. Okay, because the entire path consisting of a number of Carnot cycle A to B and B to A, and each Carnot cycle summation of heat absorbed and heat released, that part is 0. So A to B del Q reversible by T plus B to A del Q reversible by T, this is equal to 0. And this path A to B means this is path 1 and B to A means this is path 2, right? So what I can write from here? From here I can write it A to B del Q by T path 1 is equal to minus, if I take it to that side, that is B to A del Q by T path 2. Okay. This I can write. So, from here I can write A to B del Q by T path 1 is equal to, I can write here A to B del Q by T path 2. This is minus of these things, so I can write these things. So therefore, entropy change in path 1 is exactly same as that of entropy change in path 2. So entropy change delta S is same for path 1 and path 2. Therefore, entropy change delta S depends only on initial and final state, not on the path, not on path. So it is clear that entropy is state function. Entropy is state function. So it is proved. Now, our next topic is relation between entropy and internal energy. Okay, so entropy and internal energy. Let's see. Now, from first law of thermodynamics, we know that, what we know? That Q is equal to, or you can write, if I write a small change, del Q is equal to D plus del W. Okay. Now, when we are putting the condition, when this process reversible and only PV work, that is pressure volume work, PV work is involved. Then what can I write? I can write here del Q reversible is equal to D plus P dV. Right? Now from the second law, we know that entropy change, small amount entropy change, ds is equal to, that is del Q reversible by T. Second law of thermodynamics, right? So from here I can write it as this del Q, I am writing always the capital Q, no? So del Q reversible is equal to T delta S. Say it is equation number 1. So this is equation number 2. Okay. So now this I'll put it here. Putting the expression of del Q reversible from equation 2 to equation 1. Then what we can write? TdS is equal to d plus PdV, or we can write d is equal to TdS minus PdV. So this is important relation. This is the combination of first and second law of thermodynamics. So this is the combined equation of first and second law of thermodynamics. Okay, so this is the relation between entropy and internal energy. Now, our another topic is entropy and enthalpy. All of us know, already I have discussed in my earlier videos, enthalpy or heat content H is equal to E plus PV. Okay. Now you differentiate. So differentiating the equation. What we can write? From here I can write it as dH is equal to dE plus PdV plus VdP. Okay. Just now we have derived dE is equal to TdS minus PdV. Now putting this dE in this equation number 1, this expression of dE in equation number 1. So putting the expression of dE in equation 1, then what we are getting? Then we are getting dH is equal to TdS minus PdV plus PdV, this term PdV plus VdP. So PdV getting cancelled. So the relation is dH is equal to TdS plus VdP. So this is the relation between this entropy or entropy change and enthalpy change. So we have discussed today 3 topics. We have proved that entropy is a state function. That means entropy change depends on initial and final state, not on the path. And we have derived the relation between entropy and internal energy as well as entropy and enthalpy. In my next video, I will discuss the entropy change in different processes. So, we have come to the end. Thank you.